And OK, so we'll get the afternoon session started. The first talk is by Alec Agarwal. We're very happy to have Alec here. We have him visit us very often. He got his PhD at Berkeley, and he has been a researcher a senior researcher at Microsoft Research, and is working in the areas of very interesting combinations of optimization and reinforcement learning. So, Alec.
Thanks very much for the introduction, and thanks for the invite. Hopefully, people had a good lunch to recover from some of Ben's polemics, and I'll try to welcome you back to the gentle word of MDPs in this talk, so things might look a little more familiar. But I think some of the concerns are going to be very similar, as many of the talks have been referring to in the morning session, which is about how do we make our reinforcement learning algorithms more sample efficient to the point where we can start maybe using them in real world applications. And I'll talk more about that, the specifics of that. But first, I want to thank my collaborators. This work was done with a number of awesome interns, postdocs, and colleagues at Microsoft Research. OK, so what are we trying to do here? So I didn't put the Go picture here, but nevertheless, it's the same story that we keep seeing all these results on the empirical side of RL, which are largely being driven by what I would call powerful generalization abilities of the underlying learning techniques we are using, such as neural networks in basically going from perception to action. If we look at what reinforcement learning theory has largely been about, a good chunk of it was about the problem of exploration, which is how do we plan to get to unknown parts of the environment, and how do we make sure that we don't take a ridiculous amount of time in doing so. In particular, like how does it depend on the number of states we have when we have a small state MDP, and so on and so forth. And those concerns were addressed quite well when indeed we have what's called a tabular MDP. But when we start thinking about the agent making observations about the real world through sensors, then what does it mean to have sample efficient exploration? The understanding is a lot more limited, although as you've already seen even from some of the talks this morning, we are actually making quite nice advances along this program, right? But the broad kind of driving agenda of this line of work has been how do we develop reinforcement learning approaches that can find a near optimal policy using a number of samples that's not crazy large, despite having to work with these complex observations about the environment. OK, and rough outline of the talk is going to be first just setting up the model and just reminding people what are some of the challenges in reasoning within the model. Following which I'll introduce a new structural complexity measure, well, not so new anymore. It's been around for a couple of years. That does give a broadly unifying measure of RL problems that we can hope to solve in a sample efficient manner. I will describe a sample efficient algorithm, and then further start talking about computational concerns and other assumptions. OK, so let's start by describing the model. The model looks very much like a Markov decision process, although I take a lot of liberties when I say the word state in general. So I don't necessarily mean it as some sort of physical state of a system that really characterizes all you ever want to know about the system. It's really some object that allows us to induce good policies, good value functions, and that's all we care about. But formally, it will still be helpful to have the MDP framework along with us, where we think of there being some initial distribution over these x's. I usually prefer to call these x's observations, but you can call them whatever you want. We take some actions, we observe some rewards, we observe a new state or new observation. I will make the Markovian assumption here that the transition only depends on the previous state, and this process repeats, right? So I'm making a Markovian assumption. I will look at episodic problems, meaning the interaction does terminate after some fixed number of steps, denoted by capital H. And I'm going to also just to not torture you with a lot of subscripts, I will make the simplifying assumption that the process is what's called layered, meaning the set of states we can encounter at each step h in the process are different. You can just think of it as you took your original notion of state and augmented it with a variable, which is a time step, which is important because in these episodic processes, we usually need to otherwise make our value functions and policies non-stationary, and I prefer to just work with stationary ones. Right? So that the setup is clear to people? Okay, and the main thing we want to make sure, the main question we're going to focus on is we don't necessarily think of there being 10 possible indices of the values x can take, but x is just going to be some high dimensional feature vector that gives us windows into the current state of our agent. Right, and even though this is a very simple picture, I find it useful to keep in mind really when we think about these very grid worldy problems, right? So this is very classical in the reinforcement learning literature to have the agent's maybe path planning problem as simplified as this discrete grid where each cell in the grid denotes the agent's state and the agent has 4 navigational actions and maybe is trying to get somewhere. Of course, when we are maybe thinking of these things more in a real setting, we don't get this simplified grid world view of the agent. We are often, really receiving some first-person observation about where the agent is from some sort of maybe head-mounted camera, and we are trying to optimize our reward as a function of that. And we'll find it useful to have both the views in our mind so that we can interchangeably go back and forth as appropriate. Now, why is this problem difficult? That's a useful thing when you start thinking about any problem. This is difficult because so far I have told you absolutely nothing about any structure that these x's have, right? Each possible x could basically denote a completely different type of dynamics and completely different type of rewards in principle from another x. And I've told you that the universe of these x's can be frighteningly large. Right, and if really you have such a problem, then it's equivalent to saying that there is no real structure to the MDP. It's really like a exponentially large best arm identification or multi-arm bandit problem. And with that intuition, you can very easily show that there is an exponential in horizon lower bound in terms of sample complexity needed to find a good policy. Right, and this shouldn't surprise everyone because I'm really telling you nothing about the structure of the process so far. Right, so the main thing we would like to understand is we all have this intuition that this is difficult. Question, Chaba?
I was just noting that it's linear in the states. It's good.
Fair enough. Yes, it's linear in the state dimension. Unfortunately, that's a bit too large for most of our liking here. So the question is, are there notions of structure that can help bring this down? And that's going to bring us to this Bellman rank. So just as a quick primer, let's remind ourselves of Bellman equations. Okay, so and in particular, I'm maybe writing a slightly non-traditional Bellman equation here. So let me just help you parse it. So okay, so we are given some function f. This function really is we are hoping to approximate the optimal value function in an MDP using f. Right. So f is a candidate for q star. Think of if you're trying to do path planning, q star would be the shortest distance function, and f is our candidate for some possible shortest distance function. Then Bellman equations are self-consistency equations. They say that the prediction you make at this time step and the prediction you make at the next time step should be consistent with each other. So if you think you're 10 steps away from the door now and you take a step towards the door, you should be 9 steps away from the door. And that's kind of what's written here. One thing that's very important is this property holds for all possible inputs, right? So this is really, if I gave you the shortest path function, then you can ask about the distance to the door from anywhere you like, and it will always be self-consistent. And because it's self-consistent on every individual x, it's also going to be self-consistent for any distribution over x's, right? So when I think about really taking distributions over these observations, I can basically execute any MDP in the any policy in the MDP for a few time steps. It brings me to some distribution over observations. I don't care what that distribution is. Whatever that distribution is, I should have no Bellman error under that distribution if f truly was q star. Now the other thing we should keep in mind is that for these Bellman equations, okay, so there are two quantities here. There is pi. Pi is basically serving the role of inducing a distribution over my x's, because I take h minus 1 steps in my MDP according to pi, and that induces a distribution over the observations I'm going to make at step h. Now I'm going to take two actions according to my greedy policy. There is an f. I'm going to take two actions according to the greedy policy. Why greedy policy? Because if you think about f being q star, I would want to take actions according to pi star, and that's when I would know that I have no Bellman error. If I took some other random action, in particular at ah plus 1, then I'm not going to be self-consistent anymore. I can take other actions at ah if I like, but just for simplification, let's keep ah and ah plus 1 according to pi star or pi f for a general f, and we will take actions according to any policy we like for the first h minus 1 steps. Right, so you can think of this is a very commonly used way of certifying whether some candidate function is close to q star or not, reasoning about the Bellman errors of functions. Right, so that's the quantity we'll also focus on in this talk. And intuitively we want to think about a very simple kind of skeleton of an algorithm, which is pretty common again, which is somebody gives you a class of functions. So think of this being linear functions if you're a theorist, a deep network if you do things more empirically. Whatever you want, you have a class of functions, and you hope to find an approximation to q star from that class. So here is a very simple template. Okay, take some function from that class, check whether it verifies Bellman equations for all possible policies and at all steps or not. If you found a violation, that function cannot plausibly be q star, you throw it. Right? Now, okay, so all possible policies is a bit too many. I might not have a way of executing, even accessing all possible policies. So I'm going to make a simplification here, which is I'm just going to think about greedy policies with respect to the value functions in my class. It turns out this is really sufficient in our setup. So we will just check Bellman equations for pi equals greedy policies induced by functions in my class.
Do you assume that your function class is closed under greedy?
There is no function class. So I'm just taking a value function class and I'm defining a policy class here associated with it. Right? There is no policy class a priori. Does that make sense?
So there is an equivalent between the function class and the policy class.
Yes, basically the function class is inducing a policy class here.
Okay. So the question is it closed under greedy?
No.
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 So why is it? Okay.
Right.
You'll answer the why later.
Okay. I am going to assume that q star lies in this class in a moment, but I'm not going to make any like closed under Bellman operator type assumptions here. Okay, but even at this point, for this like pretty common template of an algorithm, there's a very obvious challenge that stares us in the face, which is really even if you gave me one function f, verifying whether it violates some Bellman equation or not requires checking a whole lot many equations. It requires checking equations that are linear in the cardinality of f. without any additional structure again. And again, without any additional structure, there is actually no easy way to share data amongst these different equations that you'll be required to verify. So that's kind of another view into the hardness or the lower bound that I mentioned earlier, which is even just verifying this equation for one function is going to take a lot of samples without making some structural assumptions. Right, and that's kind of disappointing because we would really like to take big function classes, and this says that you can't. And the other way to again, at least I keep thinking about it is that really, at least when you think about one particular function, you're really thinking about like a bandit problem, but with exponentially many arms, where exponential is in the horizon. Okay, but if checking these Bellman equations is the source of our difficulty, then it also suggests a path to an efficient solution. And that's going to be this Bellman factorization condition and Bellman rank definition that I'll now introduce. So let's define a matrix first, because we want to talk about ranks. So the matrix it's a gigantic matrix. For now, let's just think of f as finite, although you can kind of think of it as an operator otherwise. Things will still roughly make sense. So if you have an fg entry of this matrix, what it says is take your first h minus 1 steps according to the greedy policy of G, and then under the induced distribution, verify the Bellman error of f at step h. Okay? So this is a matrix. Now I'm going to assume that the rank of this matrix is small for all the different values of h. I'm going to give it a name. I'm going to call it Bellman rank. Okay? So that's kind of easy to do. You can define a quantity, you can name it, but is it interesting? Does it allow us to do something? So the first observation, which is kind of useful to make, is that it actually covers a bunch of what we think of as tractable or easy cases for reinforcement learning. So kind of whenever you're trying to do something with a large number of states, always a good sanity check is to say what happens when the number of states is small, right? So okay, good news is that the Bellman rank of the matrix is always bounded by the number of states in the MDP, and that should be kind of that's pretty natural, because the Bellman error of while we have too many different state distributions in an MDP, you can just think of the Bellman error under any state distribution as a function of the Bellman errors I have on individual states, and then you're just taking linear combinations of those things under some coefficients, right? So that kind of directly implies that the rank is small for when the number of states is small. But it turns out there are other interesting cases, like if the rank of the transition matrix is small, like if you have some sort of state aggregation type structure going on in your MDP, or if you have, for instance, Mengdi was talking about making linear assumptions on the transition operator, basically you're getting a factorization assumption on the dynamics that immediately bounds the Bellman rank. Pablo?
Is it reverse true? I mean, that direction, yes. But is it ever the case that somehow the Bellman rank is small and the dynamics doesn't factor?
Very good question. So, so there is a one interesting example, which is LQRs, where in fact, so one way of thinking about this, right? When dynamics factor, I can guarantee that no matter which class f you use here, the rank will be small. Now, something very interesting happens in LQRs, which is if you give me an arbitrary value function class, I cannot show that the rank is small. But remember, as I've defined it, this is both a function of the MDP and the class f I'm using. And for LQRs, when you use the quadratic value function class, which still contains the optimal value function, you get the rank is order d squared. But if you plug in some crazy value function class, I don't know how to show that the rank is small. So there is actually something beyond just saying that the transitions are low rank. And we have some other cases that we also discuss in the paper. We really try to go through a lot of examples of these structures. But I do agree that like the transition the transitions being factored is maybe the most intuitive way in which you get this?
I mean, the reason why I ask is, in the LQR case, it's never the case. Right?
Yeah.
No, no, somehow, no, no,
Yeah.
You have somehow the error, no, no, it's always somehow full dimensional.
Yeah.
No, no, okay, no. Even if there's no situation somehow where, no, no, we can actually solve something with a reduced rank. Right? The only case is when you have an observability or,
Right,
you know,
right.
or something like this.
So wait, I'm not sure I fully follow that. Okay, let's talk offline. Okay, so at least like yeah, for the factor transitions thing again, like one way we can think about this, going back to our simple description from before, is that if we are in situations where we have this complex system, but it's well approximated by a discrete system, then something like Bellman rank allows you to depend on the number of discrete states while making decisions and actions in the complex world. Okay, so that's good. It's a quantity that's maybe small in some interesting problems. Does it enable efficient learning? And that's the next thing I want to tell you about. And for this, we again need to do a little bit of thinking because okay, so what we really want to find is we want to find a value function which induces a good policy. And what we hope is that because we've assumed that this Bellman rank is small, it's going to maybe allow us to now check all these Bellman equations in some sample efficient manner. But remember, we don't know like the basis under which the Bellman matrix factorizes. We just know that one exists, right? So we still have to figure out some way of doing active exploration in a way that like basically this is like its own kind of matrix completion problem, if you want to think about it that way, right? And we have to figure out what allows us to do solve this matrix completion problem. It turns out there is a pretty simple algorithm that allows us to do it, which is just using a lot of again classical ideas from reinforcement learning. It's an optimistic algorithm. It's an iterative algorithm that basically successively eliminates bad value functions from our function class. Okay, so it's an enumeration driven algorithm. It's not computationally efficient. What it does is it starts from your original function class. Now it goes and asks everybody, it's going to use the principle of optimism. So it's going to say, under my starting state distribution, what is the value you think your greedy policy will give me if I play it out? Right? So everybody reports a number. I believe the guy who gives me the largest number. So that's good, but I should verify that number. So I execute that policy. I check if my optimistic belief was correct or not. If it seems approximately correct, then I'm happy. Why should I be happy? I just told, I'm going to assume when I give the formal theory that one of the functions in f is q star. That function would have replied truthfully to me, and whatever I found was promising me a higher value than q star. So I should be happy, right? I've basically found a near optimal policy.
Are you assuming that V hat is the correct expectation?
Well, there's a tiny epsilon there, but for ease of thinking, you can just think of epsilon being 0 for understanding why the arguments work. Everything works with finite samples.
You have an oracle that estimates, like a deep neural net, whatever, that gives you an estimation.
Yeah.
And it might, even when you give it P star, will overestimate its value.
Oh, it's going to be an unbiased estimate because this is a Monte Carlo estimate I obtained by executing the policy in the environment. So it's always unbiased.
The high probability might be biased. Being unbiased doesn't say much. With high probability, you can get a great estimate. Right?
I'm not sure. I'm just talking about convergence of sample mean here, right? I'm executing a policy in the environment, a fixed policy.
Okay.
I'm going to look at the average return it gives me.
On how many samples?
I'm going to execute 1 over epsilon squared many trajectories.
So many projects is fine.
Yes. I'm going to use however many trajectories it takes. But the overall sample complexity is going to be fine still. Okay, and now the interesting thing that we can do is, if our optimistic belief failed, then first of all we knew that this function ft was an impostor. It was not q star because it violated our Bellman equation. We can show that if anytime you violate this, you must be violating the Bellman equations. So we can throw out first of all ft. But we can, while we are at it, we can also throw out. So this is kind of one useful trick you can do, which is you can once you've collected data according to some pi t, we can use its state distribution along with some uniformly random actions to actually evaluate the Bellman equations of every function under the distribution induced by pi t. And you do that, you discard all the ones that are suboptimal, that violate the Bellman equations, and you set ft to be the set of surviving functions. Chaba?
I guess maybe the confusing thing about the way the algorithm is written is that the second bullet point says collect trajectories, and then I think that when you're estimating the expectation, you're also collecting trajectories, right? It's the same thing, right?
Yes, except here I need to just execute the policy.
Right.
Now, when I do this, what I have to actually do is I take x steps.
I'm talking the
No,
first
the
bullet.
first
Oh,
First bullet.
First bullet point only requires data at the first level, right? So this data I can collect just once. It just requires the distribution of x at level 1, and everything else only depends on f.
Okay.
So this
F is predicting the values.
right. So yes, I'm not looking any deeper into the MDP for the first step. I'm only looking at the first time step. But yes, that's a yes. Okay.
If you drop the first step and just take ft to be any surviving policy, will it make a difference in the analysis?
Yeah. I have examples where that's going to have an exponential sample complexity. So the optimistic part is actually important. Basically, the way you think about it is that you're doing like this, at least with. So in the exact case, it will be fine. In the approximate case, when we have. So if you could get all expectations exactly, it works to take a random one. When you start acting with noise, it's kind of like you're trying to make progress in something like the ellipsoid method, and it matters how close to the center you cut. And
How do you compute V-hat? So I thought at the beginning you said that you're taking 1 over epsilon squared.
No, V-hat just requires x's at the first step from the initial state distribution. That's all V-hat requires.
But you're saying it's brittle. That's what I think maybe the concern. Like what happens if there's error
Yes, there is going to be error in V-hat.
you don't actually need to maximize. You just so somehow there's a difference between the exact maximum, the approximate maximum, and what's
Sure.
left in the class.
Yes. So we are going to do. I guess we are going to do exact maximum of the sample statistic here. I'm just trying to be accurate about what we are going to do, which is exact maximum of the sample statistic, which is going to be an approximate maximum, and that's fine. That's fine. I can control how approximate that approximate maximum is by again like making sure I collect roughly like 1 over epsilon squared many samples, and that's going to be fine for the theory. Yishai still looks very confused. Okay. Okay. We'll chat later. Okay. So, but no, the algorithm does indeed like the pieces do fit together. What you can show is that if Q star is in the function class and the Bellman rank of the process is at most m, then we will find an epsilon optimal policy with high probability using a number of samples which has the usual suspects for the most part. It's got 1 over epsilon squared, some dependence on horizon and number of actions. The interesting thing is that the number of the Bellman rank basically pops up in the place where you might have expected maybe some dependence on the number of states in a classical bound. And there is this additional factor for the complexity of the function class that pops up, but it's at least somewhat familiar. It's kind of similar to what you would pay if you were doing, let's say, regression with a finite function class. So that's at least sort of compatible with what we think about complexity notion for supervised learning. Right? So that's kind of, that really says that this notion of Bellman rank is now giving us something useful because it captures a lot of problems which we think should be, in principle, easy to solve. And whenever it is small, we have an algorithm that will actually learn in a sample efficient manner. Now, the other thing you might ask is, I gave you an enumeration driven algorithm, can I actually make it computationally tractable? Unfortunately, the answer is no. Okay? So what I can prove is, so Olive induces certain constrained optimization problems. These optimization problems are indeed non-convex in F, but more damningly, even in a tabular setting, which we know how to solve in a computationally efficient manner, the optimization problems induced by this algorithm can be really hard to solve. And the basic culprit for why that happens is that, in tabular setting, like one thing that is very nice, which you do is when you are exploring, like, I don't care if which path I got to a state through, right? If I saw a sample at this state, I go and update like my reward and visitation counters associated with that state. So I sort of, even when I'm executing policies which are giving me mixtures of states, I can sort of break it apart into the individual states I'm seeing. We can't really do that here when we look at these Bellman error constraints, which are all, this is really long way back. So these guys are all basically averages. Okay, never mind. The Bellman errors are all expectations under pi, your role in policy. And because you only ever see the averages, it turns out you not reasoning about the individual states you encounter in that average can lead to some really pathological computational situations. So that's kind of depressing. We got all excited. We're like, we're going to conquer the world with this idea, and then we don't have a way to make it practical. So we'll go back to the drawing board, and the first natural thing to ask is, okay, can we make a little bit more in the way of assumptions to guide us towards a more practical algorithm? And this kind of trying to really double down on, maybe a bunch of situations where the Bellman rank is small. It's small because of the structure in my dynamics operator. So let me just really assume that. Okay. So what I'm going to assume here, this is a very like latent variable model type assumption now. I'm going to assume, so I have these, remember I have these two views of how my agent sees the world. I'm going to really think of this as a latent state which emits an observation. I'm going to assume that different latent states emit, have different supports of emission distributions. Okay, so that's kind of a strong assumption. It really says that there is this block structure in my process where I can look at a block and associate a block of observations and associate it with a latent state. Right? So in particular, this assumption implies something very strong. It is implying that there is a mapping from observations to latent states, right? Because this is just whose support are you in. Of course, this mapping is unknown. The other thing which it implies is that it really enforces the process as Markovian in both the latent states as well as observations. So you could have you could not have any partial observability. You can call it as a big MDP or a small MDP, but it's going to be an MDP in both cases. The nice thing about the small MDP is the small MDP smart people told us how to solve many years back, so we don't have to reinvent that. If only we could figure out how to go from this big MDP to the small MDP. But it's not at all obvious. Like I tell you that there is a mapping that exists between two objects. Well, it could be not even identifiable for all intents and purposes, right? So we have to ask ourselves, can we do this? Can we learn this mapping without making some other crazy assumptions about the world? And indeed, like you in the past, both sort of in the some theory as well as empirical literature, we can see people often try to do clusterings of their observations to try and interpret like a cluster as a state, right? So that's kind of one where you're thinking maybe the distribution has this very nice geometric structure to it. We don't necessarily want to make these assumptions that are geometric, so we're going to make a different style of assumption. Everything I'm going to tell you about is easiest to think about when the dynamics are deterministic first, and then I'll tell you there is a more general way to think about it. But let's just first think of our transition operator as being deterministic. What I mean by that is when you're in a state and you take an action, your next state is a point mass over, so there's not going to be any stochasticity in there. So what we'll do as an algorithm is we'll do a step-by-step starting from the time step 1 all the way to the bottom of the MDP. At every step, I will do two things. I will first construct a mapping at a step from my observations to latent states, assuming that I know the mapping at the previous time points. And then I will just continue this process lower. Okay, more concretely, what I'll assume is for now, let's just think about one level H in the MDP, and let's say we are given some collection of policies where one policy reaches one latent state with a reasonable probability, maybe as large a probability as is humanly possible in that MDP. Okay, so we are given such policies. We take some actions according to each policy, and then we roll in for 8 steps according to each such policy, and then take one action uniformly at random. Now we make some observations about this process. So first is, when I think about, remember I am assuming each policy, for every state I have a policy that gets to it. So it's as if when I'm taking my actions, I know what my latent state at level H is, right? Because I know which policy I invoked, I know which state that policy reaches, right? So I effectively know my latent state at the previous level. I also know the action I took at the previous level. Now if I think about the distribution of state action conditioned on my current observation, well, because of the Markov assumption, it only depends on my latent state at level H plus 1. And because my dynamics I assumed are deterministic, this distribution again is going to have disjoint supports for different latent states, right? Because for each SH plus 1, it just points to the parents of that latent state in my dynamics. What that means is if I could construct these objects somehow, I could just cluster them, and clusters in these objects, as opposed to geometric clustering, would really give me the unique latent states at level H plus 1. And the final observation that brings this whole thing home is you can actually basically write down regression problems to estimate these distributions, because these are posteriors. Well, not quite posteriors. These are sort of backward probability measures. But the point is these are going to be if you do a regression to the previous state action from the current X, then you will, the mean of the Bayes optimal regression function is exactly going to give you this probability distribution. So that kind of tells us that we have this object that if we could cluster, we would find latent states, and there is a way to construct this object from samples. And now that's all for deterministic. But now if you sort of boost your assumption to pretty much exactly say that, okay, what's good about deterministic is that these guys, these mapping from SH plus 1 to the previous state action, clusters very nicely. So I'm just going to assume that that's true, even in a stochastic case, and we can show examples where that's going to be true. So as long as I'm guaranteed that, I will learn a mapping from my observations to latent states using a number of samples. That is, don't be scared because I wrote a poly here. It's not the bad kind of poly. It's a good kind of poly. Like, not probably nothing bigger than a power of 3 in any term, and it's going to make H calls to a regression oracle. Basically, one call to a regression oracle at every sample. Every step. So that means we can actually now really implement this algorithm, right? And we did. Okay, we have not done anything fancy. This is a pretty simple set of experiments designed with the idea to stress test exploration, right? So for people who are familiar, there are these combination log type problems. Think of this as a version of combination log, but where you have like additional noisy observations that are clouding your judgment. Okay, and because we have these two views of the world, like there is a latent state MDP and there is an observation driven MDP that we see, we can actually really ask what happens when we run tabular algorithms on the underlying latent state versus our algorithm on the observation it receives. And in particular, what happens when we run naive algorithms with the tabular state versus good algorithms with the tabular state versus our algorithm, right? Where do we sit? What's the price of this function approximation that we're going to pay? So on the left, I'm showing one experiment where we used a linear function approximator for the regression problems that we're going to solve. And what we see is that, okay, if you do, so on the plots here on the x-axis, I'm plotting the problem difficulty, which in this case the horizon and the dimension are both related in this, so you can vary both simultaneously. And on the x-axis, on the y-axis, I'm plotting basically number of samples it takes for an agent to solve the MDP, where I define solve as you sort of getting close enough to V star. Okay, and what we see is that okay, we have three algorithms. We have our algorithm in black. We have the dashed blue line, which is Chi-Jin's optimistic Q-learning, which we know is a provably correct algorithm for the tabular setting, and it's going to be run on the underlying tabular latent MDP.
Which one, green or the blue?
Blue.
The blue is also Q-learning?
Blue is Q-learning with UCV. So this is Chi-Jin's.
And green is Q-learning?
Green is Q-learning with epsilon greedy, right? So our favorite bad exploration algorithm to beat up on. So you run the green one. It does kind of do something for a while, but as the horizon starts to get large, predictably it gets worse quite fast. This is a log plot, so we really see that the sample complexity is linear in the log or exponential in the horizon. For Q-learning, whereas we are nicely polynomial and tracking the really idealized tabular algorithm quite well. We can make things more interesting by going to harder function approximators. In this case, we used, I think, just like 2 or 3 layer neural nets, so nothing too fancy. But we asked how far we can stress the identifiability assumptions in this by adding progressively more and more noise to our observations, where at some point, like, the observation was becoming pretty damn useless. And what we see is that when the noise is small, our method, now we have 3 lines corresponding to our method, all these 3 solid ones here. For low noise, they are basically it's the same story, but as you start adding noise, stuff is getting harder and harder, which does mean that there are some limits beyond which we won't be able to do this recovery quite well. And when that fails, our algorithm certainly will fail. Okay, so I'm out of time. Wrapping up, basically we've been thinking a lot about how we can develop a general set of theoretical tools for discriminating between easy and hard exploration problems in reinforcement learning. We found some ideas that lead to practical algorithms in certain cases. We've also recently worked on extending these ideas beyond just value function based learning to model based learning, showing certain separations between model based, model free, and things like that. I think the big question here is, okay, so we have now some set of problems for which we can develop some computationally efficient algorithm, but how far can we push the limits there? So that's all I wanted to say. Thanks for your attention, and if you're interested, these are the 3 papers on which the material today was based.
Hey, any questions for Alex? Any questions? Yes.
So you had like the grid world example running along. So there the Bellman rank is small, Can you show that?
Well, if the tabular process approximates the actual MDP in which the agent is acting well, then the Bellman rank will depend on the size of the grid. Now, if it turns out, for instance, that you have like really weird discontinuous dynamics in the agent's observation space, where like you're standing and you move like a hair's breadth to the right, and your world collapses around you, then the Bellman rank is going to be horrible. So it's not always small.
Okay, let's thank Alec again.